In this subchapter 2.5, we learn about peer-to-peer applications. After that, we learn video streaming and content distribution networks. And finally, in this chapter, we'll learn about circuit programming with UDP and TCP. This one is pure P2p architecture. This one is different from client to server architecture. Here, P means peer. Peer means equivalent. Let's look at this one. No, always one server. In the client server model, always the server is running. But in this model, in this architecture, no, always one server. Arbitrary end systems directly communicate like this, directly. Peers are intermittently connected and change IP addresses. This one can be used as a peer, one peer, then it can change its IP address. In the client server model, server's IP address, that is almost fixed, but here this can be changed. This IP address may be changed. For example, file distribution, we learn about later Bittorrent. And the streaming, Cancan, and VoIP, Skype. Those are examples using peer-to-peer architecture. Before looking into the P2p architecture, let's look at this analysis. This one is rough or general conceptual analysis about the file distribution. And this one is comparing the time delay to complete that file distribution in the client server model and in this peer-to-peer model architecture. Let's look at this question first. How much time to distribute the file? The file size is F. From one server to n peers. Let's think about this one. This one is a server in the client server model, and this one is distributing file. That file size is F to all of the clients. Then how long does it take to complete that file distribution? And later we'll compare. Here they are distributing, and the peer upload and download capacity is limited resource. And here, let's look at this literal. This one is upstream server upload capacity. Here, upload means from the server to the network, that direction. And this one is uploading. This client is uploading. And this notation is simply explaining about that upload and the download, the speed, that rate. Also this client 1, the uploading rate is U1 and the download rate is D1. We can use those variables to analyze. As I mentioned, this DI means downloading capacity, and U means upload capacity. And this one is network with abundant bandwidth. In terms of the bandwidth, it is enough, sufficient enough. And let's look at this client server model first. How to complete, and how long does it take to complete that file distribution? Here, this one is server, and as we use that notation in the previous slide, here those are being used here. Server transmission must sequentially send n was upload and file copies, and the time to send one copy, it will take this time, and this is the file size, this is the rate. Thus, if we are dividing, then we can find out the delay time to upload. And this is the n copies there are n copies here because n client should get that file. And we should simply multiply this one with n, then we can get this value. That is the total delay time. And in terms of the client's view, each client must download a file copy, because here to complete each one should get that file, thus that should be downloaded. And here we can use another notation variable here, downtime minimum. Here down speed minimum, that is bottleneck and that will take a long time, thus we should consider that client. Minimum client download rate. There's the speed is lowest one. The bandwidth, the rate is lowest, thus it will take long time than others. Minimum client download time will be like this. Thus the time will be longer than others, because that is a kind of bottleneck. F divided with this the minimum. Then we can simply and roughly we can derive this equation. This is the time to distribute app to n clients using client-server approach. Thus the notation is like this: client-server model, delay time, and that will be the maximum among these two values. One is first one here. If we are considering the time at the server's point of view, then it will take like that. But if we are considering the client and the slowest client and the speed is lowest one, then it will take time and that will dominate. Thus this one will be the maximum in that case. Then we can simply choose maximum delay is dominating the total downloading time to complete that download. Thus we can choose. And if we are considering number of the clients, the variable n here, n, then it is increasing linearly depending upon the number of clients. And let's look at other architecture, P2p architecture. Simply we can compare how long does it take to complete the same mission. The mission is to distribute the one file to all of the clients in this network. And let's look at this one. Server transmission must upload at least one copy. First, as we did already, server should upload at least one copy. Time to send one copy. How long does it take? Simply we can divide with this speed. Then we can get the time. How long does it take to upload one single file? Then client. Each client must download file copy. Here, this one is uploading just once at least. Then that copy will be copied again by the other client or peers. That is the main difference between client-server model. Thus, even though this one is uploading once, that copy will be copied by other client, and that is sending to other client. Then it is working like a server. Thus, this client can work as server at client first, and later, if that received one complete copy of that file, then it can send to other peer or client. Then it is working like server. Thus, it is working client as well as server. Clients as aggregate must download NF bits and maximum upload rate. That is limiting maximum download rate is this one plus this one. Thus, this time and this one is actually the speed, the rate, the whole rate. If we are considering the upload rate altogether aggregated, summed, upload speed, upload rate, then this one, and we can simply add the others all together. Then that is the upload bandwidth. And then we can derive this equation as we did already in the previous slide for client-server model, but this one is for peer-to-peer model. Time to distribute the F file, size F, to end clients using P2p approach. Thus the notation is like this. Time delay, P2p model, and that will be the maximum because the slowest one is the dominating. Thus we are finding out the maximum time delay. Then that will dominate the whole delay time. Here, first one, as we derived here, that can be used. And the next one, this one, slowest one, that is also dominating, that may dominate. Those we can enumerate here. And finally, this one, NF width. If we are considering the aggregate size of the file, and from the network to the clients, the size will be NF, and the download rate is, or upload rate is this. Thus we can simply divide like this. Then that will be the another delay, but the slowest one among these parameters, among these delays, that will dominate the whole successful and the completion of that delay time. And that is explaining the delay time to complete the file distribution successfully, and we can choose among these delay time, and the maximum will dominate. Thus we will find out that in this aggregate and approximate equation. Also here we are considering the number of the clients, then this one is the number, and depending upon the increase of this number, and it is linearly increasing, and also the capacity, as each peer brings service capacity. Thus anyhow they are the factor is denominator, and here those are being used. Anyhow, we'll look at the final result. Anyhow, this one is providing some general and conceptual overview about the two architecture. One is client-server model, and another one is P2p model. Which one is providing the better performance depending upon the number of the clients? So let's look at this one. If that number of the clients, the number is increasing like this, then this one is client-server model. And the assumption is like this. Upload rate, as we used already, and we can assume some specific value, and it will take 1 hour like that simply. And we can assume like that simply. And this one is P2p architecture. This one is client-server model. Depending upon the increase of the client number, that is linearly increasing continuously. But in this P2p model, even though that is being increased, the number of clients are increased like this. This one is almost approaching to the certain values that it becomes to be asymptotically approaching to this value. Thus it is not increasing like this. Thus it is almost saturated here, and This one is the main difference between them. This is the time delay. Then which one is fast? This one is more faster than this one. If that the number of the clients are increasing, then this P2P architecture is much faster than this client-server model. That is the main advantage of the P2P architecture. Okay, let's move to the next. Here, this one is explain about the P2P file distribution, and this one is using Bittorrent Protocol. And this file here, that is divided into 256 KB chunks, and the peers in Torrent send and receive file chunks. Here we should understand the definition of each terminology here. Here tracker means this is tracking peers participating in Torrent. Then what is the Torrent? Torrent means a group of peers exchanging chunks of file. Then this group is called Torrent. They are attending to exchange chunks of file in this group. Then that is called, in other terminology, in other word, Torrent. And this one is tracking peers participating in this Torrent. Some information about that. And here, let's assume Alice is arriving here, and this computer is not connected yet, but this one is participating in this Torrent, and this computer doesn't have any file information, file chunks actually. And anyhow, as our real world, newcomer can attend in this P2P Torrent. Then this computer should get that information from this tracker, because this one is holding that information about that. That is about the IP address and so on. And then after that, okay, let's look at this one. Alice arrives, obtains a list of peers from tracker, and begins exchanging file chunks with peers in Torrent. Initially, this computer doesn't have any file chunks, but later this computer can get from some peer, some other computer. Then after that, she can also, her computer can send as a server to other peer. And after aggregating many chunks together later, finally, this computer will get the final complete file. Okay, then let's look at a little bit more in detail about that. Peer joining Torrent, as we observed in the previous slide, has no chunks, but will accumulate them over time from other peers, and registers with tracker to get list of peers, connect to subset of peers, neighbors. Those are neighbors, and this computer can get information, that file chunk, from neighbors. While downloading, peer uploads chunks to other peers, and this computer is downloading from others. If that chunk is a single complete chunk, then after that, this computer can upload that chunk to other peers. Peer may change peers to whom it exchanges chunks. And this terminology, churn, means peers may come and go. Peers may come and that is interacting with others later. Thus that this kind of churn. Mixing. The milk to make cheese, the milk will be mixed and stirred. That is called churn. Once peer has entire file, it may, that is a kind of selfish attitude, it may selfishly leave or altruistically remain in torrent for other peers. Let's look at a little more in detail about this Bittorrent protocol. This Bittorrent is requesting and sending file chunks. Requesting chunks. At any given time, different peers have different subsets of file chunks. And periodically, Alice asks each peer for a list of chunks that they have. And Alice requests missing chunks from peers. In that case, rarest first algorithm, because that is more important. It is not easy to get this rarest first. In that way, Alice is acquiring the complete file. Sending chunks, that is a kind of tit for tat. Alice sends chunks to those 4 peers currently sending her chunks at highest rate. Other peers are stopped by Alice to not receive chunks from her. And that is explaining the protocol, how the protocol is working. This is the time interval. Reevaluate top 4 every 10 seconds. The good neighbors are evaluated. Thus, evaluate top 4 every 10 seconds. Thus, choosing good neighbor after the evaluation of top 4 layers, top 4 neighbors in every 10 seconds. And every 30 seconds, randomly select another peer to find out another neighbor, and another peer, that means starts sending chunks. Then that neighbor is optimistically unchoke this peer. That neighbor is lucky because that neighbor is contacting and get along with this Alice, that neighbor. Newly chosen peer may join top 4. There's one neighbor that was bad neighbor that is expelled, and instead of that neighbor, another new neighbor joined into that 4 neighbor group. Like this, 4 neighbors. Bittorrent. This one is explaining Bittorrent protocol, called the tit for tat. Here, first, Alice optimistically unchokes pop. This computer should find out another new neighbor. In that way, the protocol is running. Instead of these fixed neighbors, this is the mechanism to find out new neighbor in this way. And then this Bob is sending some response. Alice becomes one of Bob's top 4 providers, and Bob reciprocates. And this is also Bob is maintaining 4 neighbors, and Alice becomes one of them, one of that neighbors, 4 neighbors actually. Let's look at the operation of Bittorrent protocol. This is called the tit for tat. First, Alice optimistically unchokes Bob, and this Bob is chosen as a new neighbor of this computer, Alice's computer. Alice becomes one of Bob's top 4 providers. Bob reciprocates responding. Bob becomes one of LEC's top 4 providers. This one is new neighbor, and before that, those 4 neighbors are evaluated and re-evaluated. After that re-evaluation, and bad, worst neighbor, that means there is no information, and the time delay for interaction that is too bad, that is chosen and that is expelled. Instead of that, new neighbor is chosen, and these 4 new neighbors are new neighbor group. Okay, in that way, the protocol is learning. Here, higher upload rate, find the better trading partners, get file faster. Thus, when this computer is re-evaluating the speed and the information, how frequently they can be got from that, and the speed, higher upload rate, depending upon that factors, the good neighbor will be chosen after that re-evaluation. Okay, let's move to the next. Next chapter is about the video streaming and the content distribution network, CDN. That acronym is the CDN. That is 2.6 of chapter. Video streaming and the CDNs. That is very successful in the real world business, like Netflix. Video traffic, major consumer of internet bandwidth, and Netflix, YouTube, those traffic is around 40% and over around 16 or 20% of downstream residential internet service provider traffic. And this statistical value is old one. Already over 1 billion YouTube users are using and subscribing YouTube video, and among them around 80% those users are holding YouTube account. And here, as of today's statistical value, the Netflix users are around 200 million, and those users are spread in the world in over 190 countries. The challenge is then scaling. The scaling means growing the volume scale. The scaling here, challenge, that is scaling. How to reach 2 billion users. In this case, that should be changed to 2 billion. Single mega video server will not work, and because of the heavy traffic. And the challenge is, another challenge is heterogeneity. Different users have different capabilities. For example, wired versus mobile bandwidth reach versus bandwidth per, so various and so heterogeneous in terms of that bandwidth. And the service provider should solve that problem. And the solution is distributed application level infrastructure. Let's look at this multimedia video. The characteristics of video, that is sequence of images displayed at constant rate. For example, 24 images per second. And the digital image is a kind of array of pixels, each pixel represented by bit. And the coding, about coding, this one is using redundancy within and between images to decrease the number of bits used to encode image. There are 2 ways. One is spatial and another one is temporal. Spatial means within that image, and temporal means from one image to next there will be some difference. and this one is explain about that. Spatial coding mean example. Those are explain about the coding scheme. One is spatial coding. Both of them will be used. Instead of sending n values of same color here, same color, right? Instead of sending all of them here in this way, that will be sent with minimized information. To simplify that the number of bits, send only two values, thus color value and number of repeated values. Then it will be more simplified. Instead of sending all real values, this simplified will be sent. And another one is temporal coding example. As we learned, video stream is composed of many images. Here 20 images per second or 30 images per second, like that. Then between that frame, I frame, I plus 1 frame, there will be some repeated values. Here this one is explain about that. Instead of sending complete frame at I plus 1, this one is sending only differences from frame I. This one is sent already. There's after that, when this one is being sent, instead of sending whole row new values, there's only the changed information. That values will be sent. Then that will be the compressed one. This one is still explaining about the multimedia video. And here constant bit rate is video encoding rate that is fixed. And variable bit rate, here video encoding rate changes as amount of spatial temporal coding changes, as we learned in the previous slide. And there have been many compression encoding schemes. Here MPEG-1, motion picture export to groups standard. First one, that was used mainly for the CD-ROM, and the speed is 1.5 megabps. And after that, MPEG-2, that was used for mainly DVD instead of the CD-ROM, and the range is between 3 megabps to 6 megabps. In the YouTube, and we are using a lot this MPEG-4, often used in internet, and we are using this one. This one is more compressed and effective, thus we are using this one. Streaming stored video. Simple scenario is like this. This is a kind of streaming application. Here, simple scenario. Here, video server. This is stored video that will be distributed through this internet to the client. That will be downloaded in that way. This one is explaining about the streaming multimedia, especially DASH. This DASH that is being used by Netflix, and this one is not being used by YouTube. This one is one example in the real application, and this one is called dynamic adaptive streaming over HTTP. This technology is using HTTP protocol. That means it is using TCP. Here, server is dividing video file into multiple chunks, and each chunk is stored encoded at different rates because the end-to-end delay from the customer's computer to the server then may be different and time varying. And this one is using manifest file. Actually, this one is providing URLs for different chunks, URLs of different chunks. That means depending upon the end-to-end throughput, the delay time may be different and the speed is different. Thus, depending upon that situation, we need to use other video clips for the proper quality. And the client, should periodically measures server to client bandwidth. Thus, this client should be more intelligent if we are trying to use this dash scheme. Usually every 4 seconds, one chunk is being downloaded from the server to the client. Thus, automatically that is being measured and evaluated. Thus, after that time-varying throughput that is different from time to time. Thus, different chunk URL will be given here in the manifest file that will be used. Consulting manifest file, as I mentioned, and requesting one chunk at a time, depending upon that evaluated throughput. Chooses the maximum coding rate sustainable given current bandwidth, and also this scheme can choose different coding rates at different points in time, depending upon that available bandwidth. That means end-to-end bandwidth between this client and the server. As I mentioned, this scheme is being used by Netflix. This dash means dynamic adaptive streaming over HTTP. Thus, this one is using TCP, as I mentioned. And intelligence is looked at the client, and this client determines when to request the chunk, so that buffer starvation or overflow does not occur. And what encoding rate to request? Higher quality when more bandwidth is available. There's depending upon that evaluated current throughput, the proper chunk and the proper rate that will be used. And where to request the chunk? Can request from URL server that is close to that client or has high available bandwidth. And in the next slide, that the CDN, Content Distribution Network, and that server will be shown later. Content Distribution Network challenge is same here and here, but optionally we can choose one of them, option 1 and option 2 for the same challenge. Option 1, single large mega server. We need that to distribute that content for the worldwide service like Netflix or YouTube. This is not possible because the scaling up is not possible. Single large mega server is not being used because this one is the reason for that. Single point of failure, one reason, and another reason, point of network congestion, that may be a problem, and the long path to distant clients, also that is another problem, and the multiple copies of video sent over outgoing link, and that is another inefficient problem. Anyhow, this centralized server, mega server, that scheme is not good because that is not providing that scaling up service. And the content distribution network, still we are learning about this, and the challenge is same challenge, and optionally we are using usually this CDN scheme. Store, serve multiple copies of videos at multiple geographically distributed sites. That is called the CDN, Content Distribution Network. And we are using these two schemes. Depending upon that, the price and the delay time, those are different, but let's look at this one. Enter deep scheme. This one is pushing CDN servers deeply into many access networks, and that is deep. That means close to users, and that is being used by Akamai and over 1700 locations in the worldwide location, and that is more expensive scheme. And bring home, that is holding smaller number, for example 10, a couple tens of larger clusters in point of presence near access networks, but not within access network, and that is used by Limelight and this one is a little more inexpensive solution, but the delay time is a little bit slower than this. Still, we are learning about CDN, but let's look at this Netflix example. For example, here Netflix stores copies of Mad Men movie, and this customer wants to watch that movie, and in the world those servers are distributed in the world like that, and nearest server will provide that. Subscriber requests the content from CDN, and directed to nearby copy retrieves content like this. After certain period of time, if that is being congested, the network is not so good anymore, because that network condition is always time variant, and depending upon the situation, they may be congested or disconnected. There's alternatively other, even though that is not nearby, that may be used. May choose different copy. If network path congested, this one is congested, then we can use that. And this one is explaining about the over-the-top scheme. Usually Netflix service, that kind of service is over-the-top service, and simplified acronym is OTT. OTT service. Netflix is providing OTT service, and OTT service is because of this. The others are here below this, and above HTTP in the application and layer, above application layer. This one is being implemented there, and HTTP protocol that is located in application layer, and this one is using that over that HTTP. Let's look at this one. Ott challenges, copying with the congested challenges, congested internet from each CDN node to retrieve content, and the behavior in presence of congestion. Depending upon the congestion, congestion may be happening, and this one is using, Netflix is using HTTP, that she is using HTTP because that is over the HTTP, and the HTTP is using TCP. TCP is using that congestion control, and if that congestion is happening, then that this one should serve that using the TCP protocol. From each CDN node to retrieve content, behavior in presence of congestion, what content to place in each CDN node. Those are challenges to provide their good quality of service to the customers. And CDN content access. Let's take a closer look here. This scheme is used by YouTube. If this one is even though this one is explained here, that is not being used by the Netflix. This one is being used by YouTube, even though that is not described here. POP, let's assume POP is okay. Here requesting video HTTP, and that video URL here, that video ID here, and that video is stored actually in DC CDN, and the CDN, and that video code is here, and here we are using, okay, let's follow this procedure. First, POP gets URL for video HTTP, this one, from netcinema.com web page. Bob is watching that web page, and he is linking and clicking that one to access that video. Then this one is working in that sequence, and this one is sent to the Bob's local DNS server. That is same in other case also. Resolve this URL to get the corresponding IP address by a Bob's local DNS server. And then this one is asking iteratively here. Then this NetCinema's authoritative DNS server, this one is providing the information. Usually this one is providing the IP address, but instead of that IP address, this one is providing another URL, and this one is holding that video, and that is also being used in other porting services by the domain registration companies. And instead of IP address, that the URL is given to this one, then this one should resolve again. There's here resolve again that given domain name, the URL here actually, and that King CDN, that is King CDN here, and this one is the authoritative DNS server, and this one is holding kingcdn.com IP address, and that will be used. And this one is providing that information to this local DNS server, and this one, the IP address of this King CDN, that will be given to this Bob's computer. Then this one is using that IP address directly request the video from King CDN server, because this one, this client get that information already. Thus this one is establishing TCP connection using that IP address, and this one is getting that data directly from this server. And this one is using TCP and HTTP. This kind of scheme is being used by YouTube. Thus Netflix is not using this scheme. Next one, this scheme is being used by Netflix. Let's follow this procedure. Bob is subscribing Netflix, and he manages Netflix account, and that account server is here. And this one is the Netflix registration accounting server. And Netflix is using Amazon Cloud. Here, web pages, and those web pages are holding some manifest information here. Those are stored there. And Bob browses Netflix video here, and he is requesting, and manifest file returned for requested video from this Amazon Cloud server. After that, directly from corresponding and the recommended CDN server, that file will be sent to this. Thus, the video streaming using this dash stream is done here. This one is used by Netflix, and this is the case study for that. Okay, let's move to the other topic. And finally, in this chapter 2.7, about the socket programming with UDP and the TCP. I showed you using the real Python code, and if you are looking at that Python code, then it is easy to understand. Here's socket programming. Goal is to learn how to build client-server applications that communicate using sockets. And the socket means door. This is door. Through this door, we can send and receive. Door between application process and the transport protocol. And usually this process is controlled by application developer, and this one is usually embedded in the OS or controlled by operating system. Socket programming, two socket types for two transport services, as I showed using the real example of Python code. UDP, that is unreliable datagram. TCP is reliable. And anyhow, we learn about these transport layer protocols in the next chapter, chapter 3, in detail about them. Reliable byte stream oriented protocol. Application example is this. As I showed you already, client reads a line of characters from his keyboard and sends data to the server, and lowercase character, then that will be sent to the server, and the server receives the data and converts characters to uppercase simply, and the server is sending modified data to the client. Then client receives modified data and displays line on its screen, as I showed you already using the real example using the Python. In that case, I use the Visual Studio Code, and also you can use Visual Studio Code or Python integrated development environment, depending upon your choice. You can implement in any way. Socket programming with UDP. UDP, this one is providing no connection between client and server. There's no handshaking before sending in the data. Send explicitly attaches IP destination address and port number to each packet. This is a socket ID, including this IP address as well as this port number. Receiver extracts send IP address to respond properly. Think about your mail. You are sending to your friend a mail, then your friend will use my sender's address. That is my address, right? Sender's address. He will use that address to send. That will be the destination address to send by my friend to reply. Like that. Receiver extracts sender's IP address and port number from received packet to send that reply. And that address will be used for the destination address later. UDP transmitted data may be lost or received out of order. That is a kind of characteristic of UDP protocol. We'll learn in detail about this in the chapter 3 later. Application viewpoint. UDP provides unreliable transfer groups of bytes that is called datagrams between client and the server. Let's look at this one. This one is explaining a little more in detail about our example code. Client server socket interaction. UDP case first, later TCP. Server, that is learning. With the server port number, initially we are creating socket and the port number here using the socket function, and that server socket will be created this way. And the client side, the client is creating socket like this similarly, and the client socket will be created. And this one is creating datagram with the server IP and the port number X. Send datagram via this created socket through that socket, and that will be read by the server. Through that datagram is coming through the server socket, and that will be read. And after that, that will be used to change it to uppercase characters, and that will be sent as a reply. Through the server socket, that will be sent, and that will be arrived, and here the server is using that client socket, and through that client socket data will be read and shown on the screen, and after that the client socket will be closed. Okay, this is real example using Python code. Python UDP client here. This one is including Python socket library. And after that, this one is localhost or IP address if we are using remote server. And server port number, any number below 2 to the power 16 because this one is using 16-bit. That means 65, 535. That's the maximum number, but usually higher number, the same number. In our real Python code, I use 22,000, the number. This one is creating UDP socket per server in this way. Address family internet socket datagram. This means UDP, and the client socket will be created. After that, this one is getting low data that is typed in by myself or by the customer, by user, input row get sentence, and this is waiting for that, and the user will type in, then that will be LED. And this one is client socket is sending that message and the server name and the server name and the server port number together, because that is socket ID. And that modified message and the server address, like think about your mail contents, mail envelope, that is address, destination address to send properly to your friend. And that will be sent to in this way, and receive from this one is receiving primitive method, primitive function, and this is the buffer size, and through this client socket we can receive. And finally the modified one, that means the uppercase character string, that will be received, and finally that will be shown on the screen, and after that will be, this client socket will be closed. Okay, this one is explain about that. And let's look at UDP server side, server program using the Python. From server, okay, socket import, and this one, same port number, and create UDP socket here, and the binding socket to local port number here, and this one is looping forever to provide a service to any customers requesting this service. This one is receiving from the this client, and through this server socket, and changing to uppercase, and that is the change the character string variable name for that, and that will be sent to the client through this server socket using this primitive method. And let's look at this TCP case. This is very similar, and I already explained it a real example, Python code. Client must contact the server. Server process must first be learning, as we learned already and observed already. Server must have created a socket, that is door, that welcomes client contact. Thus, this one is called the welcome socket. And the client contacts server by creating TCP socket, specifying IP address, port number of server process. That should be same as I mentioned and as we observed. When client creates socket, client TCP establishes connection to server TCP. And when contacted by client, server TCP creates a new socket. That is another one created whenever the new client is requesting. Then depending upon the client request, this one is being created. For server process to communicate to that particular client, allow server to talk with multiple clients. And source port numbers used to distinguish clients. And the different client may be differentiated using that port number. And we'll more in detail in the chapter 3, that is the transport layer related to this one, and explaining in detail about this. Application viewpoint. TCP provides reliable in-order byte stream transfer, that is called the bit pipe between client and server. Let's look at this interaction like our previous UDP example. Server. This one is learning first. Before that, this one is creating socket. That is welcome socket. And this one is waiting for incoming connection request from the client, and that is called connection socket. Here we can create that. using this accept method or primitive function here. And the client is requesting after creating socket, and this one is creating socket, and this one is making that TCP connection setup, and this client socket will be created. And after that, through the client socket, this one is sending some data. In our real example, some lowercase input by user. Through that client socket, that will be sent to the server, and server is reading that request from the client that is coming through this connection socket, and finally this one is changing to the uppercase character string, and that will be sent through that connection socket. This connection socket is related to that corresponding client socket, and another client is requesting here again through that welcome socket, and this another connection socket will be created. Thus, if there are 10 clients are requesting, then actually here one welcome socket and 10 connection sockets will be created. Thus 11 sockets are created in server side. Okay, this one is showing the Python TCP client program. Here, this one is creating TCP socket per server, remote port number. Here, a number below 65535, including that number. We can use that big number as server port number. Here, please be careful about this sock stream, that is for TCP. And here, after using this one, client is creating client socket, and using this one connect to the server, and after that this one is waiting for that input from the user, and that is a lowercase character string, and this sentence, that variable name is holding that, and that will be sent to the using this client socket and this primitive method. And after that, this one is receiving the converted character string, converted to the uppercase character string by the server, that will be received using this receive method, and that will be assigned to this variable name, and here the result will be shown out using this one. And after that, the client socket will be closed, but still the server side that is running here. Let's look at and observe here. Create TCP welcoming socket, that will be created first. This is called welcome socket. Here server socket is binding to the server port number, and this one is listening any request from the client, and each client will be serviced. Here, if there is any request from the client, then this one is looping forever and waiting for that request from the client, and this one is accept that request, and after that that welcome socket and that object is using this accept method to create this connection socket for each client, and this receiver per 2K byte, 4K byte, doesn't matter, and the received one through that connection socket, the character string will be changed to uppercase, and capitalize the sentence that variable name is holding that character string, and that will be sent through that connection socket. After completion of that conversion, this connection socket is being closed, and this one is explain about that. Okay, this is the summary about Chapter 2. Our study of network application now complete, and the application architecture we learn, client server and P2p model. And the application service requirements, we need a reliable, and we need the bandwidth, and the delay. Those performance issues also we consider. And internet transport service model, there are two kinds. One is connection oriented and reliable, and unreliable datagram UDP service. And the specific protocols, we briefly learn about that. This HTTP first, and SMTP, POP, IMAP about email protocols, and the DNS domain name system protocol, and the peer-to-peer Bittorrent is one example for that. And in this lecture today, we learned about video streaming, content distribution networks, and we just learned about socket programming briefly, TCP UDP sockets, and some example using Python. Most importantly, learned about protocols. Typically request reply message exchange, client request information or service, server response with the data status code, and message formats, headers and data. Think about HTTP header and data. Fields giving information about data. Data is the main information. In other words, that is called the payload. That terminology is from telephony technology, because when we are talking about something, then that is being paid, and that is called payload. The other action, like you are calling people the main call message, then that is overhead, but the real calling time to talk, that is called payload. Important themes: control versus messages, in-band, out-of-band. That concept is not explained here. Later I will explain about this, in detail about this. And centralized and versus decentralized scheme, state rich versus stateful, reliable versus unreliable message transfer, complexity at network edge. That is about the application layer, and we'll go into the transport layer. Transport layer is layer 4 among 5 layers. We just completed the layer 5, that is the top layer.